250 मिल Good morning, everyone. Today, let's begin with our session. But before that, if audio and video both are fine, please let me know. Great, wonderful. So let's begin with our session. So in today's session, what we are going to do is first a small topic that was left from yesterday class, that is about applications of nuclear technology. So we'll first finish up this particular topic of applications of nuclear technology, and then after that we will look at some of the questions from the mains examination from the chapter of energy. So all the questions that have come in the past few papers, we'll have a look at them, and then after that we shall move to our next chapter, and which is the chapter of space technology. So this is what we are going to do in today's class. Now, the very first thing about applications of nuclear technology. Until now, when it comes to nuclear technology, we have understood that there are various ways in which this technology can be applied, whether through nuclear fission or fusion or radioactivity. These are ways in which we can make the use of nuclear energy. Now, largely what we understood is that this is where we are trying to focus on energy that is especially in terms of electricity, right? So most important application of nuclear technology is electricity, and electricity generation, whether with the help of uh, nuclear fission or maybe with the help of nuclear fusion. But this is what our primary objective is, which is this is what our primary goal is. Now, overall, when it comes to applications of nuclear technology, apart from electricity being the primary goal, no doubt about that. All right. So most important application of, I would say, electricity, and this is what we have been discussing through nuclear fission and fusion. But apart from that, we do see that there are other ways also in which we can make the use of nuclear technology, and that too in various different sectors. So what are these? Let's try to understand that. First, all the agricultural applications. Now, in case of agricultural applications, what we understand is that it can be used in water use and soil management, in pest control, in ensuring animal health and productivity, and in ensuring food safety. Now, in all these cases, what we do is that we use controlled amount of radiation. All right. In all these cases, controlled radiations are used. Controlled radiations are used so that if anything, any microorganism, any decomposer is causing some kind of problem to these crops, or let's say the fruits or the longevity of the seeds, in all these cases radiations can be used to kill those microorganisms, and by killing those microorganisms we can ensure that they do not harm these crops in any way, or even food productivity in any way. So this is something that we have to understand from that perspective, that controlled use of radiations will be done so that any microorganism can be killed. Now, apart from these, what we also have is something called as nuclear fertilizers as well. Nuclear fertilizers, and especially this is the case of nitrogen 15. Now, normal nitrogen is nitrogen 14, right? But this is nitrogen 15 with one extra neutron, and nitrogen 15 is something that we use as a nuclear fertilizer. Now, what we mean by nuclear fertilizer is that this nitrogen 15 is radioactive, not really harmful as such. You cannot say that every that radioactive element is harmful, but nitrogen 15 is used as a fertilizer, and nitrogen 15 most importantly helps us in determining what is the correct amount of fertilizer to be used for a certain crop. So we are able to determine how much fertilizer should be used for a certain agricultural crop with the help of nitrogen 15. So it helps us in optimizing the fertilizers. All right, it helps in optimizing the fertilizers. So what happens is that how much of fertilizer should be used for a certain crop, that can be determined very well with the help of nitrogen 15. So that's why it becomes crucial from that perspective. Similarly, it is also useful, nuclear technology is also useful in carbon dating. Now, when it comes to carbon dating, this is something that has allowed us to accurately date historical artifacts. So anything that is up to 50,000 to 60,000 years old, that can be that age, their age can be perfectly determined with the help of carbon dating. So carbon dating is where we use carbon 14 to understand what is the age of any fossil or anything that we have discovered. Now what happens here is, just understand this, that how carbon 14 is actually useful here. Any material that we have, anything that we find, or any, let's say especially any organic matter, has a fixed ratio of carbon 12 to carbon 14. All right, so they have a fixed carbon 12 to carbon 14 ratio until they are alive. So until they are alive, what happens is that overall carbon 12 to carbon 14 ratio will remain fixed in them. But after they die, new carbon 14, so new carbon 12 is not added anymore, and carbon 14, being radioactive, will start to decrease in its quantity. What happens is that for any radioactive element, because it will be losing out particles automatically, naturally, that's why it will keep on decreasing in its quantity, and in some time its quantity would have decreased. Now every radioactive element has a fixed time period in which its quantity might decrease. There is this concept which is called as half life. Half life basically is a concept where we talk about the time period in which a sample of radioactive element decreases to half of its original mass. Meaning that if you have 100 grams of carbon 14, how much time does it take for it to decrease to 50 grams of carbon 14? Now, half life, for example, of carbon 14 is almost 5,700 years. So we see what should have been the exact value originally and what is the value that we see today. So depending on that, a calculation can be done to find out how much time would it have been, so that carbon 14 value has decreased to this much. So in this manner, what we do is, by determining carbon 14 value, we are able to understand how much of time it might have taken for it to reduce to this particular quantity. So overall, this is how we look at application of nuclear technology in carbon dating. Then there are a lot of industrial applications. Now, in all these industrial applications, we are able to analyze the strength of the material in a lot of ways. So whether it is about non-destructive testing or enhancing the material quality, in all these cases, we see that we can analyze the strength of material. So again, this is where we see that there are some radioactive elements that become very, very crucial from that perspective. And overall, when it comes to industrial applications, we see that especially in these industries, we are able to even enhance the quality of the products. We are able to enhance the strength of the material as well with the help of certain radioactive elements. So that is also something that we can do. Then there are there are medical applications. Now in case of medical applications, what we see is that we most importantly use it in radiology, where some radioactive elements have been seen to have good medicinal properties and they can be used in medical therapies. For example, we have in case of cancer. In case of cancer, what we observe is that we can make the use of radiations from radioactive elements, and this can be used to kill cancer cells. It can be used for killing the cells that have started growing with growing without any leaps and bounds. So in that particular scenario, what we observe is that in all these cases we can make the use of all these radioactive elements. So there we see that in radiology, again, controlled amount of radiations will be used to kill the cells which are causing cancer. So in this manner, in especially in case of medicines, we can make the use of radioisotopes. Then apart from that, we also see that there is something called as radioisotope thermoelectric generator that is useful in space exploration. Now overall, when it comes to this called as RTG, this is something that ISRO has started constructing, and almost 2 years back they had started constructing this. So this is where we'll see that we can make more or less, you can say, something like a battery, something like a nuclear battery, where they will be useful in space missions, especially the space missions that are going deep into space, that are going towards the outer solar system. Because when you are in the inner solar system around the earth, around let's say Mars and moon, etc., in all these cases there is a strong presence of the sun, and hence the solar energy is very, very useful in all these kind of missions. But as we start going away, as we start moving towards the outer solar system and outer space, this is where solar intensity will also start to decrease, and because of that, solar energy will not be uh, available with us in a quantity that is useful. So this is where we see that nuclear technology can become very crucial, because then you can make the use of all these nuclear technology, and I mean you can use the energy from nuclear technology to fuel all these missions. So here what we see is that a radioisotope, which is plutonium 238, becomes very, very crucial. So these are some of these applications. Now what I've also done for you, and I'll ask the team to share the document with you. I've made a document with all the important radioactive elements, all the important radioactive elements and their applications. Please go through it. This can be important for you, especially from prelims perspective. So the most important radioactive elements, what are they and what is their use? So I've just compiled a list of all these. So it is factual, you just have to remember a few of them. It can become crucial, but just go through it. All right, just go through it. I'll share the same with the team here, and the team will definitely share it with you. So this is the end of this particular chapter. Now before we move on to the next chapter, also let's have a discussion on some of the previous year question papers with regards to the this particular chapter, that is energy. Now, energy as a chapter, you will find that this is a chapter where questions, a lot of questions were not coming in the past. I mean, if you analyze the question papers, suppose before 2015, you will not see that a lot of questions have been coming, whether at prelims level or at mains level. Not a lot of questions. But now we see that the world has a very different view, and India also has been pushing a lot for all the alternate sources of energy, whether it is solar or wind energy, or whether it is hydrogen today, or whether it is nuclear energy, any form of energy. We see that there is a big push towards these kind of sources which are alternates to coal and petroleum. Now in all these cases, that's why we see that because of so much of discussion happening around it, so many new schemes and policies coming into the picture, this is something that makes this chapter now very important. And that's why most of the questions that have come, you'll find that the questions have been coming only in the last 6 7 years. So whether at prelims level or at mains level, this is where the number of questions have started to increase. Now when it comes to the mains examination, and if we look at some of the previous questions, before we go there, there are some things that I also want to discuss with you with regards to writing of your answers as well, especially in the context of science and technology. And not only science and technology, I would say GS paper 3 in general. When it comes to GS paper 3, this is a paper which is, you can say, a bit more technical than the other papers. You have science and technology, you have environment and ecology, you have economy. All these are areas which are a bit more technical as compared to the other papers that you have to write. So here, when you are attempting such a paper, there is a slight change in your strategy while your answers are being written. And this strategy, most importantly, has to hover around examples, data. If you can use examples and data in your answers, it will really well substantiate your answers. And that is something that we very often see is also lacking in many of the answers that students submit to us. That you, let's say, give the information very well, you explain the things very well, but you don't substantiate your answers. And in this paper, I would say that substantiating the answers, giving examples, giving the data to the answers becomes very, very crucial because of the way the construction of this entire paper is. Whether economy or science, you'll or even environment, you'll see that always there are reports, always there are new examples, there are new things happening, there are a lot of data, numbers being presented. So all these things, they should be a part of the answer. And many a times we see that the answers that are submitted, they are very generalized answers, and hence they do not add value to the answers. Now in case of GS1 and GS2, what happens is that there is a limitation that there aren't a lot of examples or data facts or etc that you can use in your in your answers. But in GS paper 3, there is a scope, and you'll find that more often than not, in one question or the other, there will be a way in which you'll be able to represent something which is a new example or a data that was reported in some kind of a new uh, let's say article or a report that was published. So that's why you should always ensure that you are using those to your advantage. Now overall, so that's why let's look at some of the questions that you have here. First question is, do you think India will meet 50% of its energy needs from renewable energy by 2030? Justify your answer. How will the shift of subsidies from fossil fuels to renewables help achieve the above objective? Now, this kind of an answer, always remember that when you look at the first question, first part of the question, it asks you, do you think India will meet 50% of its energy needs from renewable energy by 2030? Now, these kind of questions, the answer is never yes or no. You cannot say that yes, India will achieve all the targets required, or you cannot be no, 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 India can't achieve the targets. You can neither go complete positive nor you can go complete negative. You have to be very, very balanced in your approach. You do not have to say yes or no. You have to first present the present state. Where are we? What are we doing? What are the targets? What are we doing to achieve those targets? What are the schemes and policies which will help us in achieving those targets? And then we can see that, okay, fine, if all these things, whatever we see, we do see that we are moving in a positive direction, we are doing well with regards to all these, and if we keep moving in this direction, then I'm very sure that we'll be able to achieve the targets that we have set for 2030. So you have to go this way, instead of directly saying that yes, everything is good and everything is fine, or saying that nothing is going right. You have to take a balanced approach here while presenting your answer. That you have been That's why you have been asked to justify your answer. That whatever you are saying, whether you are saying yes or no, you have to justify why you are saying yes or no. And please don't say no in these kind of answers. But you don't just have to go into the praise of what is happening and thinking about, okay, if I write a very positive answer, the government is going to give me extra marks. Nothing all like that happens. You have to justify your answer, and at the same time also present the facts in your in the favor of your argument. So so what we'll do is, in this kind of a scenario, we'll give a basic introduction first. A basic introduction will have to be given, and this introduction should not go beyond 30 to 40 words. All right, this should not go beyond 30 to 40 words. You talk about that this is the present state of India, this is where we are, and all that. And then after that, start analyzing in your body. When you go to write the main part or the body of the answer, this is where you will start talking about all the various sectors, all the various energy sources, and what are we doing to get to this answer, to get to this target. So this is where it becomes very crucial that you also mention all the schemes and policies. All the schemes and policies, they should be mentioned well here, whether it is the national solar mission, or whether it is the rooftop solar which was in news just yesterday, or whether, let's say, it is the green hydrogen mission, or national offshore wind energy policy. So there are so many things. All right, there are so many things, and there are all these schemes and policies that we have. National biofuel policy we had discussed. So there are all these things, and you'll have to mention all these, that how exactly these are being used to get to the required target. And then the second part of the question says, how will the shift of subsidies from fossil fuels to renewables help achieve the above objective? Now, when it comes to subsidies, subsidies is all about financial aid, correct? Whenever subsidies are being given, you are trying to help financially. So if, let's say, if the subsidies start to shift away from the fossil fuels towards the renewable energy sources, then what happens is that, in a manner, we are saying that the government is now going to provide more help to non-fossil sources than fossil sources. So automatically, the entire industry will start, or entire process will start building around renewable energy instead of non-renewable energy. And at the same time, many of the companies and many of the private firms also will be compelled to move away from coal and petroleum, because now they would also see that there is no financial help that they are getting from the government, and it becomes very cost intensive for them to keep continuing in that sector. So then what happens is that, in this scenario, they would also want to uh, shift towards the renewable. So it will not only be a policy change where in general we'll see that the financial aid to the sector will help the sector grow, but also we'll see that the private participation in the renewable sector will also start to rise. So that also has to be substantiated in your answer. So these are some of the points that you can write in when it comes to this kind of an answer. And the conclusion in this particular question should be around the future, that this is what our expectations are. And here you have to end on a positive note. End on a positive note, giving a ray of hope, I would say, that okay, these are the things that we have done, and this is where we are moving, and surely we should be able to get to the target if all these things keep moving as they are currently. So all these ways you can write about what's being done and what can be done. Question number 2. The Nobel Prize in physics of 2014. Now, this, in that scenario, we are basically talking about the invention of the blue LEDs, and this is basically just an information about the Nobel Prize. The question starts here. How has invention impacted the everyday life of human beings? So how do we see that everyday life of ours is getting impacted because of blue LEDs? Now, blue LEDs have been a big revelation because everywhere today you see blue LEDs. On your screen right now, you are able to see because of blue LEDs. So your laptops or your mobile phones, tablets, wherever you are watching the lecture, there is a backlight which is made of blue LEDs. Your housing, in your homes, probably today you are using LEDs. These are also blue LEDs. In the medical applications also, we find that blue LEDs become useful. So there are different various sectors, different walks of life where we see that blue LEDs are being used today. Now, the importance of blue LEDs mainly is with regards to their longevity and sustainability. All right. Mainly, we are talking about their longevity and sustainability. Now, we are basically talking about two things. One, their longevity, meaning that they can be used for much longer. For example, let's say if we are talking about providing electricity to the homes, compared to the fluorescent light or compared to the incandescent bulbs, you'll find that LEDs can function for much longer. One LED bulb can function for much longer as compared to these sources. So that's why longevity. Secondly, the energy saving, the sustainability factor, that it is very highly energy saving uh, source, and that's why when we use it in the houses, we see that they would be able to decrease the energy usage altogether and help us in also optimizing the electricity use. So in all these cases, what happens is that blue LEDs become very crucial from that perspective. And at the same time, I would also want you to also mention schemes that have been launched by the government. For example, the Ujjwala scheme. Now, in this scheme, what we have done is that in especially in the rural areas, the LEDs have been provided very cheaply or even for free, so that LEDs can be used by the people in the villages, in the rural areas, and that will help them in saving energy. And with the push that we have seen from the side of the government of India, we have seen that the prices of LEDs also have decreased. So that's why from that perspective it all becomes very crucial when we look at all these factors. Now, question number 3 and 4 both are related to nuclear energy. If you look at the first question, with growing energy needs, should India keep on expanding its nuclear energy program? Now, with growing energy needs, you cannot say that India should not expand the programs. So that's why the answer invariably here would be yes, that we need to keep on uh, improving upon or expanding upon our energy program, nuclear energy program. Now comes the important part, and this is about the facts and fears related to nuclear energy. Basically, the positives and the negatives. This is what you have to write here. The positives and the negatives of nuclear energy, and largely this is around. So when it comes to facts and fears, largely we know that right now we are in the phase of nuclear fission, that all our reactors are based on nuclear fission. But we also talked about the fact that nuclear fusion can become the future. So there should be a brief mention of that as well, that although we are not really using uh, nuclear fusion today, but in the future, whenever we are able to use it, whenever we understand how to commercially use nuclear fusion, it will change the entire paradigm of energy requirements, and we'll see that nuclear energy will become very very crucial from the solving the energy problems of the world. So that's why in all these cases, that's why the positives and the negatives have to be presented, and we discussed many of these points in the discussion. But overall, again, try to have a positive outlook here. And because when we are saying that our energy requirements are expanding, we cannot say that our energy program should not expand. Fourth question, give an account of the growth and development of the nuclear science and technology in India. What is the advantage of a fast breeder reactor program in India? Now, first thing is basically about India's nuclear program. So what we discussed about the three phases of India's nuclear program is what you have to write here: the importance, the requirement, all those things. And then about the fast breeder reactor, also we discussed that why fast breeder reactor is important, what all it adds with regards to uh, uh, the energy future with regards to nuclear fission energy. So all those points have to be presented in this question. Again, something that we have discussed in the classroom itself. So these are some of the questions that have come from the mains examination perspective. So as I told you, as you can see, that 2017, 18, 21, 22, there was another question that I have not written here because it was asked in GS paper 1, that was about wind energy. And the question on wind energy that came again was something that we had discussed in our science classes. So obviously this chapter is a gray area between science, geography and environment. So although question came in GS paper 1, this was 2022, a question came in GS paper 1, but the answer can be written based on the basis of all the discussions that we have done in our class here um, about wind energy. All right. So before we move on, any questions if you have anything from whatever we have discussed? In this chapter, there is some numbers and percentages often seen. Should we remember those numbers? Yes, Sham, I would say, I would strongly suggest, and that is what we were just discussing also, that when it comes to these numbers, the data and the facts, especially the latest facts, whatever comes just before the examination, I would say that they are important. They should be used wherever you can, especially in your mains examination. It becomes very crucial. In the prelims, they would never ask you those numbers directly, but in the mains examination, if you are able to use those numbers in the answers, it really helps you enhance the quality of your answer. And especially given the fact that whether in this chapter or many of these similar chapters in even economy and environment, you'll see that they become crucial. Uh, because then it shows that you have read better than others, because the general answers without the data and the numbers will be written by a lot of students when they are writing the answers, especially when, let's say, you have an easier question, because even the questions that we just saw, they were not difficult questions as such, right? So that's why what will happen here is that a general answer with general points will be written by a lot of people, but somebody who is substantiating with examples and numbers will always get some extra marks compared to somebody who has just written a general answer. So I would say that these data points become crucial. How nuclear technology helps in water use and soil management and animal health and productivity. Basically, what happens is that radiations are used first and foremost also to collect soil samples and analyze soil samples. So it helps us in understanding the nutritional level of the soil. And at the same time, with the help of the nuclear fertilizers, we can also add to the soil quality. Similarly, when it comes to, let's say, water use and water management, there also radiations can be used for cleaning and filtration of the water resources, and also to understand the data, also to understand the quality of the soil, and that also helps in the betterment of the health of the water resources. And in case of animal health and productivity, again we have seen that nuclear energy becomes very crucial in also analyzing their health, and also in terms of helping them in one way or the other, especially with regards to diseases. So they can be helpful in killing of the microorganisms as well, and that is where it comes from. but international organizations ban those products which are subsidized. So don't you feel subsidies can be hurdle as well rather than reinforcing of renewable energy? See, when it comes to subsidies for a healthy economy, it is always said that if without subsidies, if an economy can function, it's always better. But for a developing economy like India, it is not always possible to do that. And financial aid and support is required in many of the cases. For the economies that are developed economies, for them it will still be manageable because they would have those kind of resources and money to function. But here, unless there is a strong government support, many of these industries cannot function without it. So that's why I would still say that it becomes important. And we are more than international organizations and international requirements. We are talking about our domestic energy requirements. So domestically, whatever subsidies are being given to the companies functioning in the non-renewable sector, that can be extended to the renewable sector altogether and help in shifting of these subsidies internally. So we are not talking about external factors and how we are going in the international markets, but how we are trying to solve the energy requirements of India domestically. So that's why it would not be a big factor there. Can you please share the document you were talking? I will share the documents after the class. I will mail it to the support team and they will definitely share it with you. So one doubt, one KLPD value needs to be remembered while writing answers when it comes to the job creation. I'm asking this because yesterday I saw a recorded video. So all, I mean, when it comes to the expected benefits, all those data points that we had seen, they were all the data that I've taken from PIB. In PIB article, all those data were presented. So what the logic I was just talking about 5 minutes back, that's the logic that can be used in this scenario also. Because if you are able to use, I mean, see, if you don't use, it's not that there is anything wrong in not using that data, but if you remember and if you are able to use that data, it will always help you in maybe getting some extra marks in the answer, because then it looks a well substantiated answer with the data points and examples. So that's why there it can be used in the mains examination. Again, in the prelims examination, I'm not expecting those numbers to be asked. In the mains examination, but those numbers can be used. All questions were current based or were contemporary things. Largely these were about the larger topics in discussion. They have not asked any particular topic, they have not picked any particular topic, but these are larger discussions with regards to the energy needs and energy requirements. Can we write both advantages and disadvantages for every question? No, I wouldn't say that. It depends on what kind of question you have and in what context the question has been asked. So if they don't want you to write disadvantages, don't write them. Recently in the news, IT605A is the world's largest fusion reactor. Uh, see, fusion reactor wise, we see that the largest fusion reactor right now is under construction, that is ITR. And then the other one that you have is in Japan, which is, you can say, a smaller version of the same ITR. So overall, all these new nuclear reactors have been coming up. There is one in China, there is one in Japan, there is one in France, there is one in the US, and we see that there are all these competing to crack, you can say, commercial energy from nuclear fusion. What is atomic clocks and how is it related to nuclear energy? Atomic clocks basically are very precise clocks. I mean, compared to our normal clocks that we are using, these are clocks which can be very, very precise, and that's why they are very helpful in analyzing something where you need very exact time, where you need very precise and accurate time. So, atomic clocks, what happens is here, why it is related to nuclear energy is because we use cesium and its isotopes, which are also radioactive. So that's why it is related to nuclear technology. Should an IAS officer be as soft spoken as you, or should they be a no nonsense person? You actually can be both at the same time. You can be soft spoken and be a no nonsense person at the same time. So both are not actually related to one another. As long as you can get the work done, and you'll be trained for getting the work done, you know, you would exactly understand how to get the work done when you are a civil servant. How to approach a question if you don't know much about nuclear prize discovery given back in 2014 or some previous year. So the question in this context that was asked, it was not really about the Nobel Prize, but rather it was about blue LEDs. And blue LEDs have been a part of discussion for, you can say, a decade now. So this, I would not say that it was a current affairs question, but yes, if let's say a situation arises where you do not know anything about the answer, just you have to find that whether do you know anything that you can write. That let's say you have a let's say a very basic idea of the blue LEDs, then in that case just use that basic idea, that okay fine, I know that blue LEDs are being used in the households, I know that they save energy, I know that they last longer than our incandescent bulbs or the fluorescent lights. So use those kind of points. So anything that you can use, anything that you know of, instead of not writing anything. How nuclear technology improves public safety. So in case of public safety, for example, let's say even in runway lights they are used, they are also used as smoke detectors, they are used in coating of the utensils as well. So there are various ways in which these radioisotopes are used. Americium, for example, is well known for using in public safety. Hydrogen I've not discussed because somewhere around as a part of current affairs I'm going to discuss over uh, the last over the next few months. So that's why hydrogen is something that I've skipped for now, because there I'm also waiting for the budget, because in budget hydrogen will be a part of the budget in one way or the other. So after that it will become a more important topic. In yesterday's class there is a nuclear fusion topic in which there are equations. No, equations are not required, it was just to show you what happens. It's not required for the exam. For the past 150 to 200 years we are depending on coal, which reserves will end soon. Like that, if we start nuclear energy, that will also lead to exhaustion of uranium or any other material that is used in nuclear energy for future generation. This is, I mean, likely true, but also the fact that when you use uranium or when you use, let's say, thorium, so thorium usage will go on for much longer time, because you use very small amount of fuel for getting a large amount of energy. That's not the case with coal and petroleum. So that's why exhaustion will not be as quick as it has been the case of coal and petroleum. And also we know that all these, we have to ensure that we can make it as sustainable as possible. That if let's say in future when we are able to use breeder reactors much better, which is a part of India's plan anyway, so when you start using those breeder reactors or other reactor designs, where our reliance on uranium or anything in that scenario will start to decrease, and this is where the world is headed right now. Anurag, your issue I'll just ask the team to look into. Large hydrogen, no, it's not large hydrogen collider, it is large hadron collider. It's not associated with ITR, that's different. Can I skip tablet lectures after attending live classes? Yes, of course you can. Will You can just go through the classes that what we are conducting right now. It's a more updated class, I would say, as compared to the tablet lectures. Are e-vehicles also examples of renewable energy, or only of low carbon economy? I would place it more into low carbon economy, not completely into renewable, because anyway we are using lithium, which is limited in its quantity, so you cannot keep on using it forever. Just hold on for a minute. Is audio and video fine? Am I audible and the video is also working? Hmm. Great. So let's move on to our next chapter, and this is the chapter of space technology. Now, overall, when it comes to space technology, I would say that this is the most important chapter from science and technology perspective. There is no chapter that can give you a guarantee of at least one question in the examination than this particular chapter. In the prelims, we see that every year at least one question comes, if not two or three. And in the mains examination also, we see that almost every year one question does come from space technology. So that's why it makes it very important. And historically also, you'll see that this has been one consistent chapter. This, you go on and look at the last 30 years, last 35 years of question papers, you'll find that every year there is at least one question from space technology that has been asked. So that's why space technology will remain one of the most important topics from examination perspective, now both at prelims and mains level. Now overall, when it comes to this chapter, we'll divide this chapter in two parts. First will be about space science. We'll discuss about the universe and the various concepts related to the universe. And then after that, the second part where we'll discuss about space technology, about what are satellites, how do we launch satellites, what are PSLVs, GSLVs, the role of ISRO, space technology applications. So we'll discuss about all that in the second part, second half of our lecture. And the first half will be more about the theories of the universe and the various aspects related to all these celestial bodies. So this is how we are going to talk about this chapter. Now, when it comes to space technology, the first thing that's why will be about the universe. Now, when we talk about the universe, the very first thing, the very first challenge, I would rather say, is even in defining what the universe itself is. Because we know that everything basically is a part of the universe. There's nothing that lies beyond the universe. So in that scenario, how do we even define what universe is? So a very simple way to define what the universe is this: everything that exists, everything that has existed, and everything that will exist is a part of the universe, right? all the past, present, and future, everything is inside the universe. There's nothing that is outside the universe. Now, when it comes to this definition, I understand that fine, everything that exists here is a part of the universe. But why are we talking about the past and the future? Why are we saying that everything that has existed is also a part of the universe, and everything that will exist is also a part of the universe? So, in that particular scenario, what happens is that when we look at what has existed and what will exist, uh, you also have to understand that everything that exists currently in its form will not always remain in the same form. Correct? It will not always remain as how it is remaining or how it is existing in the current form. Suppose, let's say, we are talking about a star. All right, and today a star that is shining bright, tomorrow its life will also end, right? And before today, some time back, it was not a star. It was just maybe a bunch of gases which started collecting together. So its past is different, its future is different, its present is different. So that is the reason why we are saying that even in the past and the future, everything that exists is going to be a part of the universe. And here we are talking about a concept called as law of conservation of energy. Have you heard of this? Law of conservation of energy. Do you know what it is? Can somebody define it for me? Yes, Srihari, you have given the first correct answer. Animesh, you are correct. Lakshmi, you are correct. Rohit, you are correct. So now everyone is giving the correct answers. So, law of conservation of energy says that energy can neither be created nor destroyed. It can only be transformed from one form to another, right? Energy can neither be created nor destroyed. It can only be transformed from one form to another. Right? So this is what we say about law of conservation of energy. So something similar is happening in the case of the universe also, that everything that is existing, it exists inside the purview of the universe itself, just that its forms keeps on changing. Sometimes it is a star, sometimes it is just a nebula, sometimes it is a black hole, or maybe nothing, just a bunch of energy particles flowing around in the universe. So that's why everything that exists, has existed, will exist, is all a part of the universe. Now, when we look at the composition of the universe, this is where the complexity actually starts. That the composition of the universe can be divided into three parts: dark energy, dark matter, and the rest. Now, when it comes to dark energy, dark matter, and the rest, what we know is that almost 70% of the universe is dark energy. Exactly, we say that it is 68%. Almost 25% of the universe is dark matter. Exactly, we say that it is around 27%. And then we have the rest. Now, when it comes to the rest, this is where we see that the known universe exists. All right, this is where the known universe exists. So let's start with the rest first. What is dark energy and what is dark matter? Let's have a discussion on that later. But first, let's try to understand what is this rest. Now, in this rest, what you see is that 4% of the rest is just hydrogen and helium, meaning that 4% of this entire universe is just hydrogen and helium. Now, this is a big number in the context of what we know of, that we are saying that 95% of the universe is dark energy and dark matter, which more or less you can say that they are unknowns for us. We do not really know about what exactly they are. So from that scenario, we can say that we almost do not know about 95% of the universe, and we only know about the 5%. So in that context, that we know just about 5% of the universe, 4% of that known part is just hydrogen and helium. This is a big ratio, right? This is a big proportion. So overall, that is the reason why we see that this becomes very, very crucial. Now, the rest 1%, if you see, out of that 0.5% are all the stars in the universe, billions and billions and billions of stars in the universe. they basically make up they basically make up just 0.5% of the universe. Now just imagine, how many stars do you see? I mean, if you're living in a city, then probably 10, 20. And if, let's say, somewhere maybe in remote areas, then probably you're lucky enough to find and see 50 odd stars in the night sky. Correct? So not more than that. So out of billions and billions of stars that we have, see almost nothing. Then 0.3% basically are neutrinos. Now, when it comes to neutrinos are also very unique particles. And again, in this context, 0.3% is a big number. 0.3% is again a very big number here, because in the context of what we know of, now neutrinos basically are particles which we say are uh, chargeless and massless particles, or you can say chargeless and almost massless particles, where in this particular scenario, chargeless and almost massless particles, I'll just write it here. Neutrinos, they are chargeless and almost massless particles. All right, chargeless and almost massless particles. Now, chargeless means that they do not carry any positive or negative charges, just like neutrinos. Just like neutrons. In case of neutrons, also we know that they do not carry any charge, but they carry mass, right? Their mass is good enough. But compared to neutrinos, or compared to protons, or compared to neutrons or protons or electrons, the mass of a neutrino is very, very low. It's very, very low, almost negligible. All right, almost negligible. So that's why we say that they are almost massless particles. Now, these neutrinos, they largely are found in the space. They are just roaming around space. I mean, I can guarantee you that right now in your room, there are lots of neutrinos that are just passing by without you ever understanding that that's happening. So neutrinos, that's why they would just keep on roaming around the universe all across, and they have a big number. Their major source is something called as supernova. We'll discuss about supernova later. But supernova is the largest source of neutrinos. And then there are other nuclear reactions that can also lead to the formation of neutrinos. So that's why either nuclear reactions or supernova, these are the big sources of neutrinos, and neutrinos make up 0.3% of the entire universe. uh, a fact also about neutrinos is how the name actually came into existence. I mean, obviously it's not important for your examination. uh, Neutral, I mean, first it has been derived from the word neutral, and thus neutrino. And uh, the Italian scientists were the ones who actually discovered the neutrinos first, and they were the ones who had studied neutrinos very well. So in um, when it comes to, let's say, Italian, when they add ino, it means that there is something which is very small. Neutrino. So they would say neutrino, and that neutrino means that this is something which is very, very small or very, very light in weight. So hence the name coming from neutral and then becoming neutrino. So chargeless and almost massless particles. Then 0.17% you can see is antimatter and electromagnetic radiation. So antimatter and electromagnetic radiation. Now, first and foremost, What is antimatter? Now, in case of antimatter are basically particles or matter which have same mass and opposite charge. All right, particles with same mass but opposite charge. Now, if I ask you, can I say that electrons and protons are they antimatter of each other? Can I say that? Can I say that electrons and protons are antimatter of each other? Some of you have said yes, some of you have said no, but yes, some of you have given the correct answer. Satyam, Vedri, Jia, Rohit, correct. Yeah, Kavna, you have given the correct answer. Electrons and protons are not antimatter. Why? Because protons are much heavier than electrons. The mass of a proton is almost 2000 times heavier than an electron. Almost 2000 times heavier. So mass is not the same. Charges are opposite, but mass is not the same. So that's why these are not antimatter. Electrons and positrons are antimatter of each other. All right. Electrons. So for example, electrons and positrons. So positrons are particles which are said to have same mass as electron and opposite charge from electrons. So that's why these are antimatter. Electrons and protons are not, because protons are much heavier. So this is what antimatter is. So now a lot of these antimatter are very highly unstable. They do not last for very long, and they do not really exist as easily as the normal particles exist. Now, then electromagnetic radiation, we'll discuss more about electromagnetic radiation when we go to IT and communication chapter, not for now. But light, radioactive, radio waves, gamma rays, X rays, all these are electromagnetic radiations. Then the last 0.03%, 0.03% are the heavy elements. Now, when we say heavy elements, uh, our definition of heavy elements when it comes to chemistry is very different. That, for example, uranium that we discussed in nuclear fission, uranium can be called as heavy element because its atomic size or atomic mass is big. But in case of astrophysics, whenever we are discussing about space technology, etc., heavy elements basically are every element apart from hydrogen and helium. All right, every element every element apart from hydrogen and helium. All right, every element apart from hydrogen and helium will be called as heavy element. So this is basically the rest, the composition of the rest, and this is basically the part that we know of. This is the 5% part that we know of. The problem starts, the real problem starts here. Dark energy and dark matter. What do we mean by dark energy and what do we mean by dark matter? So let's try to understand that first. Dark energy. Now, when we say dark energy, we do not really mean that there are some dark forces out there. There is a supervillain out there which is responsible for that dark energy, as the movies would show you. But that's not the case. When it comes to dark energy is named as dark energy mainly because of the fact that we do not even know what kind of energy it is. We have no idea about what kind of energy it is. Hence, we named it as dark energy because we are in the darkness. We do not know what kind of energy it is. So, hence, we thought that, okay, fine, let's name it as dark energy. So dark energy is nothing to do with darkness. It is nothing to do with anything evil or anything bad. It's just that dark energy has been named dark because we are in the dark, because we do not know what kind of energy it is, hence we named it as dark energy. Now, if we do not know that what kind of energy it is, then how do we even know that it exists? So this is where we have to briefly go into the history of our understanding of the space and its composition and its structure. Now, initially, it was believed that the entire universe rather, is in a steady state. In a steady state, meaning that its structure never changes. Whatever is the structure of the universe today, it is the same structure as it was millions of years back. It will be the same structure millions of years from now. So it does not change. The structure of the universe, all the celestial bodies, their relative positions, they do not change, is what we understood initially. And this was called as steady state theory. It was called as steady state theory, stating that nothing ever changes. But then came a scientist, and I had told you yesterday also, a scientist whose name will come in every chapter, and this was Albert Einstein. Now, Albert Einstein basically, as a part of his theory of relativity, he found that the universe should not be in a steady state, but it should be expanding. The universe should be expanding. And his mathematics was showing it. His mathematics was showing that the universe is expanding. But he thought that he was wrong. He thought that whatever conclusions he has derived, these are wrong conclusions, because he was also a very firm believer that universe is in a steady state. So what he thought is that his theories are wrong, his mathematics is wrong, there is some kind of calculation mistake that he has done somewhere. And then he changed his equations. He changed his equations and made the universe steady again. So universe, he stopped universe from expanding in a manner, you can say, through his equations. So so now this happened, all right. Just almost 12 years after this came another scientist, edwin hubble edwin hubble. Now Hubble again independently proved it, that the universe is expanding, and something that he again proved it to be correct. Now, this is when Albert Einstein thought that this was a big mistake, that this, and he called that it was the biggest blunder of his life's biggest blunder, that he could have been the one to get this all in his name, but now it will go to this guy, that is Edwin Hubble. So one of the most important discoveries that could have been gone, that could have been in the name of Albert Einstein, went to the name of Edwin Hubble, because Albert Einstein did not believe in himself. He thought that he was wrong. So forget about people like me and you thinking that we are not good enough or having those second thoughts. Even Albert Einstein had them. So have confidence in you. If he had the confidence, this expansion of the universe would have been in the name of Albert Einstein. So, so now Edwin Hubble, he proved that universe is expanding. All right, he proved it that the universe is expanding. He proved it that universe is expanding. So now, uh, when it comes to Edwin Hubble and he proving universe is expanding, this was fine, that he just proved that universe is expanding. Later, what we found, that universe is not only expanding, but it is expanding in an accelerated manner. All right, universe is expanding in an accelerated manner. Not visible. Universe. All right, this was proved to be later. All right. So this was proved to be later, that universe is expanding in an accelerated manner. Now this accelerated expansion of the universe is something that should have some kind of energy behind it. For any kind of work that is being done, you need some energy to behind it, right? So there should be some energy pushing for that work. Now if the universe is also expanding in an accelerated manner, there must be some form of energy that is leading to this accelerated expansion, right? Now what form of energy it is, we do not know, and hence it was named as dark energy. So overall you can say that dark energy is the form of energy, all right? Dark energy is the form of energy that leads to the accelerated expansion of the universe, right? Dark energy is the form of energy that leads to the accelerated expansion of the universe, that is behind the accelerated expansion of the universe. So in this manner, this is basically what we discovered at a later stage, that universe is expanding in an accelerated manner, and hence anything that the energy that is leading to this accelerated expansion is dark energy. And this expansion is happening everywhere in the universe. That if you see that, if let's say you are looking at these three galaxies, the distance between them also keeps on increasing. So that meaning that the universe is expanding in an accelerated manner, and it's not only a normal acceleration. So that's why dark energy is that unknown form of energy which is hypothesized to permeate all of space, tending to accelerate the expansion of the universe. So that's why the energy that is behind the accelerated expansion of the universe is called as dark energy. So this is something that we proved, and hence dark energy was seen to be behind it. Then comes the important concept of dark matter. Now, in case of dark matter, what we understand is that this is again an unknown form of matter, hence dark matter. Now, when we say dark matter, what is the meaning of matter? We say that anything that has mass and occupies space is called as matter, right? And when it comes to matter, wherever you have matter, because it has mass, it will also have gravitation, right? It will also show gravitational force because it has mass. But even if you don't think of it, understand how we came to know that there should be something called as dark matter. Now when we were doing the calculations about various galaxies and the other things that we have found in the universe, we found that our observation, the data in the observation and data in the calculation are different. The data in the observation shows something else, data in the calculation shows something else. So they we did not understand what's why this difference. That, for example, what I'm saying is that suppose that you are in your room right now, and let's say in your room you have a table, chair, maybe your clothes, maybe your books, maybe other equipments in your room. So this is what you have observed, right? This is what you observe in your room. And let's say if I ask you to tell me the entire weight of the entire mass of your room, you might pick everything individually, and then you would tell me that this is the entire mass of this room, including the walls, including the roof, including the floors, etc., right? Let's say this comes out to be 1000 kg. But then I ask you to pick the entire room as a whole and weigh it, and you find that this entire room weighs not 1000 kg but 5000 kg. Now this is perplexing, because according to you, you have factored already for everything that you see in the room, right? So that difference comes because of dark matter. In the universe, when we do the same procedure, that difference comes because of dark matter. So this is the scenario in case of, let's say, if you are not able to find what's causing that difference in your uh, room. So that unknown form of matter is called as dark matter. So maybe you are not the only one in your room who's studying right now. Maybe there are others also who are availing the course for free and just listening to the lecture with you. So that ghost of the universe basically is dark matter, the unknown form of matter that we don't know of, that we don't understand, that we don't see, we are not able to observe, but we do see that in our calculations. That is what dark matter is. Now, until now, we do not really know what exactly dark matter is composed of. There is this mission that has been in the news, especially last year. This is the Euclid mission. Now, Euclid mission has been launched recently, Now this Euclid mission basically is for exploring. It says that it will explore the dark universe. Now exploring the dark universe basically means that it is something that is going to look for dark energy and dark matter. So these kind of news articles have been coming around it, that Euclid telescope captures unprecedented views of the deep space. So overall, this is a mission that was launched in July last year, and since then it has been taking various pictures, and very often you will see that once in a while it keeps coming back in the news. So overall, this is basically for exploring the dark universe, mainly meaning the exploration of dark matter and dark energy. Dark matter and dark energy. So that's why now we are trying to look for all this. So for example, in case of dark matter, there is something called as weakly interacting massive particles. Weakly interacting massive particles. Now, so in short, WIMP is what we call them. And sometimes you will see that even these WIMPs will also be in the news. So that's why just be on a lookout, just in case these appear in your newspaper. From prelims perspective, I would say that they can become important, because they are said to be dark matter. They are uh, right now being investigated. They are trying, scientists are trying to see whether or not they can be classified as dark matter or not. So there are all these missions and all these programs that are running to find dark energy and dark matter, to understand what is dark energy and dark matter. Now, the next topic is the formation of the universe. But before going there, if you have any doubts with regards to whatever we discussed until now, anything that you want to ask, anything that is not clear. What are boson particles? So boson particles basically are not really related to this, but these are force particles, and these are the ones, you can say in a manner, that are responsible for the weak forces inside the nucleus. Inside the nucleus, all the particles that you have, the various particles that you have, they interact and they are able to generate force via bosons. Does the space between planets in a solar system also expand? Yes, but in a very, very, very slow very slow pace. So that's why it is not something that will affect the structure in even millions of years. But eventually, it will affect it, but not. I mean, it will take millions of years before something like this can take an effect on the structure of the solar system. If the universe is expanding, then how Milky Way galaxy and the Andromeda galaxy is moving towards each other? That's also because of the gravitational effect. Look, when it comes to the accelerated expansion of the universe, the forces, the energy that is behind it, it's not such a strong energy that it will just make everything just go away from each other. It will happen very slowly. And if there are other forces that are also between them, then in that case, those forces might take us the charge, and hence it may not expand in that sense, but overall the expansion of the universe is happening. Accelerated means accelerated, so basically, see, there could be two kinds of expansion. Either, let's say, an expansion which is happening like this, all right, an expansion like which is happening like this, and or an expansion happening like this. So this is normal expansion, this is accelerated expansion. Dark matter, simply just understand, this is the unknown form of matter. Matter that we do not see, do not observe, but appears in our calculations when we are calculating the forces that we observe. So that's why, although we can't see them, but our calculations say that they should exist. The rest 4% is not clear. 4% is just hydrogen and helium. Hydrogen, helium, they make up almost 4% of the universe. What is the main difference between dark energy and dark matter? Huge difference. I mean, there is no similarity between them. Uh, Dark energy, we are saying that it is the energy that is leading to the accelerated expansion of the universe. Dark matter, we are saying that it is an unknown form of matter that is there everywhere in the space, but we can't see it. What is space time? See, in terms of space time, what we basically can say is that it is these are the dimensions in which all the calculations can be done. That when we just think of the space, that is not enough for doing a lot of calculations. Suppose when you are doing the calculation for a movement of any celestial body, then in that case only defining what the location is, or what the coordinates are, will not be enough, because there is a constant movement happening. So with space and time, these coordinates should always be considered. Does that mean that our planet is expanding, or just the space? No, just the space is between the galaxies largely is expanding. It's not an expansion that happens inside the matter. How Euclid mission can take pictures of dark matter as it is invisible? So it's not really pictures, and it's a very different scenario in which uh, all these all these calculations are done, or all the observations are done. Pictures are not always about taking a photograph. It is very different from that. So even x-ray imaging is done, radio imaging is done. There are a lot of ways in which we try to find something. Is dark matter source of gravitational waves? Can't really say that. Black holes different from dark matter? Yes, they are. George Lamenter is related to the Big Bang theory. What is WIMP full form? Weakly interacting massive particles. Explain with one more example of dark matter. So there is no example of dark matter. We don't even know what it is. We just think that it should exist. It should be an unknown form of matter, invisible form of matter that exists everywhere. Should we make these diagrams? No, not really required. What is baryonic matter? Baryonic matter is any normal matter. Anything made of protons, neutrons, and electrons, they are called as baryonic matter. What are luminous and non-luminous? Luminous means something that is illuminated, something that has a light source, and non-luminous, which is not a light source of light, that is. The interaction of ultrasonic light with dark matter will lead to, we do not know. We are not able to even observe it. What is supercrunch? This is basically a theory about the contraction of the universe. Are we going to study hypernova and supernova? Supernova we are just going to discuss in a few moments. How do they realize that there is dark matter and dark energy? Because of something that is unknown, something that we are not able to explain. That's why dark is the word that they have given, that it should be able to explain what they can't understand. All the theories are equally important? No, only the Big Bang theory is important, others are not really important. Hmm. So now we come to the formation of the universe. Now in terms of formation of the universe, there are various different theories that have tried to explain what the universe is like and how exactly the formation of the universe might have happened and how it has been going on since. Now, overall, out of all these theories, this one theory, that is the Big Bang theory, is the most important because this is the most widely accepted theory. This is the theory that has been able to explain a lot of observations that we have made about the universe. So that's why it is the most widely accepted theory. The other theories are not that widely accepted. Only one theory that I would say is somewhat important apart from the Big Bang is the string theory. So these are the two that we will also discuss. The others are not required to be discussed. The steady state theory already has been discarded. We discussed this about the fact that when we used to say that the universe is in a fixed state, that there is no expansion, there is no change in the structure of the universe, that was called as the steady state theory. Then we have the eternal inflation theory. This is a theory that talks about the concept of multiverse. The multiverse again is a concept which looks very nice in films and TV shows, etc., but not something that has been proved in the real world to be true. So eternal inflation theory is about multiverse. And then after that, oscillating universe theory and big bounce theory, the they both talk about that uh, the universe does not only expand always, but it keeps on expanding and contracting. This is what they say. Now again, uh, when it comes to oscillating universe theory, or even the big bounce theory, there aren't really a lot of things that go behind proving this to be correct. So that's why the only two theories that become important for us are the Big Bang theory and the string theory. So we'll discuss about what exactly these two theories are. Now, overall, first and foremost, when we look at the Big Bang theory, what the Big Bang theory says is that the universe was very hot and concentrated in the distant past, and ever since then it has been stretching and cooling. All right. So what it says is that it was hot and concentrated in the distant past, and ever since then it has been stretching and cooling. Now, what it basically says is that the entire universe, when the universe was formed, the entire universe was a very tiny particle, a particle that would have been even smaller in size than a proton. Just imagine the entire universe was of the size of something smaller than a proton, and this was very hot and concentrated. The temperature is said to be of the order of 10 to the power of 32 degrees Celsius. So very hot and concentrated, like a soup. It was said to be like a soup, that all the particles, all the forces, etc., they're just mixed in this entire particle, just how a soup is. So the entire universe was this small particle soup, which was very very hot and concentrated, and then expansion started. It started expanding from there on, and then it kept on expanding into the present state of where we are. So this is basically what the Big Bang theory says, that the universe was very hot and concentrated in the distant past, and ever since then it has been stretching and cooling. Now, in this particular scenario, when it comes to the Big Bang theory, the Big Bang theory has been one of the most widely accepted theory, because a lot of things that the Big Bang theory said, all that proved to be correct later on. So let's say if it was the other way around, that you had a lot of theories and you just compiled all that into a theory about the universe formation, that would have been different. But in this case, a lot of predictions were made by the Big Bang theory, and those predictions turned out to be correct later on. For example, expansion of the universe, the accelerated expansion of the universe, proved to be correct later. Initially, it was just a theory. So in 1960s, the Big Bang theory talked about an accelerated expansion of the universe. In the 1990s, we proved it to be correct. So that is one very important evidence that supports the Big Bang theory, the Hubble expansion. So Hubble expansion basically is nothing but the accelerated expansion of the universe. Accelerated expansion of the universe. This is called as Hubble expansion. All right. Now, another evidence has been Big Bang nucleosynthesis. Now, however much scary this term might look, but it is nothing but the abundance of hydrogen and helium. So this is what we discussed, that 4% out of the 5% of the universe, known universe, is just hydrogen and helium. So that abundance of hydrogen and helium is called as Big Bang nucleosynthesis. All right, simple. Now, one major evidence in supporting the Big Bang theory has been the cosmic microwave background. Now, just try to understand what we mean by cosmic microwave background. So, cosmic. Where do we use the word cosmic? What is the meaning of the word cosmic? Can somebody tell me? Space related, right? Correct. So, anything related to space, anything beyond the earth. True. So that is called as cosmic, correct? Anything related to the space, anything related to the universe is called as cosmic. Then the second term is microwave. Now, microwave basically is what? Microwave is a kind of electromagnetic radiation. For example, you might know about microwave ovens that a lot of people use in their homes, microwave ovens. So, these microwave ovens are what? These microwave ovens will help you in heating the food or maybe cooking the food, right? So, in this particular scenario, when we look at microwave ovens, they have microwaves in them, and microwaves are associated with heat. So, cosmic microwave. So, microwave is a kind of electromagnetic radiation associated with heat. And then the third term is background. Why background? Because it is something that we can observe in the background when we look at the outer universe with the help of certain instruments. Now, when you look at these three pictures right here, all right, these three pictures, uh, if you see, the first picture is a very blurry picture, then you have somewhat better version of the picture in the second one, and you have a much better view of the same picture in the third one. Now, these are three instruments that have been sent to observe cosmic microwave background. The first one was called as COBE. This was in 1993. Then the second one was called as WMAP, and this was in 2006. And then the third one was called as Planck. This started in 2009. So in this manner, we see that there have been various instruments that we have sent, various missions that we have sent to observe the cosmic microwave background. So now this cosmic microwave background is nothing but, you can say, the heat remains of the early universe. This is heat remains of the early universe. Heat remains of the early universe observed through certain special missions like COBE or WMAP or Planck, etc. All right. So if you look at this picture, so what you see right here is that if we are looking at the outer space from this end, then in the background you can see that there are so many celestial bodies which are visible, and in the background what you see is cosmic microwave background. So that is called as cosmic microwave background. This right here is called as cosmic microwave background. So, and this is a picture, let's say, of representation of the W map, that we are looking at all the celestial bodies, and in the background we can see that there is cosmic microwave background. The heat remains of the early universe just after the formation of the universe. So these three become the evidences. These three have become strong evidences supporting the Big Bang theory. And you can say more or less because of these evidences, the Big Bang theory became the most widely accepted, the most popular theory that explains the formation of the universe, and rather the journey of the universe as well. So overall, that's why we see that these all, they become very, very crucial, and hence they will uh, help in understanding a lot of things. Now, one thing you should also understand, that although we are saying that the Big Bang theory is the most widely accepted theory, it is still a theory, right? Still a theory. It is not a law. It's not a physical law. You cannot say that this is exactly how things happen. Tomorrow, maybe we'll find something new, and everything that we know through the Big Bang theory might be discarded. So Big Bang theory may not remain the most widely accepted theory if something new gets discovered. So that's why this is a process. You can say that until now this is what our understanding is. Maybe our understanding changes in the next few years, or maybe the next decade or so, and then probably we'll see an entirely new theory. So that's why you cannot always guarantee what we'll see and what will not. So for example, let's say the James Webb Space Telescope that has been sent a couple of years back. The James Webb Space Telescope has found evidences of the very first star about 65,000 years after the birth of the universe. 65,000 years after, you can say, the birth of universe happened. Now according to the Big Bang theory, the first star should only have come approximately 380,000 years later. So until the time of 380,000 years, the first star should not have been formed. But now we have evidences of the first star being there almost just 65,000 years after the formation. So we do not know whether these things can change tomorrow, and then you perhaps will have a completely different theory. Let's take a break here before we go on to the string theory. Uh, the time is 7:45, so let's be back by 8, and we shall continue our discussion from there on. Welcome back, everyone. So let's resume our session. We discussed about Big Bang Theory, and we discussed that Big Bang Theory simply says that the entire universe was very, very small and then it started expanding. Now, the second theory that we see very often in the news is string theory. Now, string theory gives a very different view of the universe. What string theory says is every particle and every force, all right? Every particle and every force that exists, they are all made of tiny strings. They are made of very tiny strings, and these strings basically make up the matter, they make up the force. Now, what they say is that what this theory says is that there are various vibrations that are produced in these strings, and all these vibrations in the strings basically basically lead to one kind of matter or the other. Just think of a guitar. That guitar also has these strings, right? Any stringed instrument like violin, guitar, sitar, etc. In all these cases, what do you have? You have strings, and as you plug the strings, there are vibrations which are produced in these strings, and various different vibrations will produce different types of musical notes. Correct. So similarly, what it's this string theory says is that the vibrations in these tiny strings will just produce different types of matter, produce different types of particles, and produce different types of forces. So that's basically what the string theory says. Now, that's why what it says is that describes the fundamental level of the universe in terms of vibrating strings rather than particles. So what it basically says is, you can say every it's every okay, let me write every particle that is matter and force is made of very tiny strings. Very tiny strings, different vibrations in these tiny strings produces various particles. All right. So this is basically what we are talking about. These in case of the string theory. Now, when we talk about this string theory, one thing that has to be understood is the reason why string theory is talked so much, why it is discussed so much, is also because of something called as theory of everything. There is something called as theory of everything. Do you know there is one scientist whose name is always taken when we discuss about theory of everything? Whenever theory of everything is mentioned, do you know who is that scientist? Yes, Stephen Hawking. Correct. So Stephen Hawking's name is always taken as a part of theory of everything, and basically what this theory of everything says is that there should be a way in which we can unify all the fundamental forces. All right. Theory of everything talks about unification of fundamental forces. Unification of fundamental forces. Now, when we talk about, I mean, this term fundamental forces, there are four forces which are called as fundamental forces. We have something called as the strong nuclear force. strong nuclear force, weak nuclear force, electromagnetic force, and gravitational force. These basically are called as four fundamental forces of nature. These are the four fundamental forces, and every other force that you know of is derived from one of these four forces. So these are, that's why called as fundamental forces, because these are not interconvertible into one another. Now, what theory of everything says is that there should be a possibility of unifying all these forces. These four fundamental forces, there must be a possibility in which we can unify these forces. So that unification is what theory of everything is, which is supposed to be one of the most complex concepts of our times, of our generation. And that's why we talk about Stephen Hawking a lot, because he has been one scientist who has dedicated, you can say, almost the entire of his second half of his life just to prove theory of everything to be correct. Although he could not, and he has given a lot of theories about it, but unfortunately he could not, and hence he does not have a Nobel Prize in his name. Uh, Probably uh, one of the greatest, if not the greatest scientists of our generation, does not have and probably will not have a Nobel Prize in his name, because Nobel Prize is given only to people who are alive. It is not given to somebody after death. So, unfortunately, one of the greatest scientists perhaps will not have a Nobel Prize in his name. So, this is what theory of everything is, that it talks about unification of the fundamental forces. And now, out of these, since we are talking about these fundamental forces, just one thing to mention, that when we look at these fundamental forces, strength wise, what we see is that strong nuclear force, strong nuclear force is stronger than the electromagnetic force, which is stronger than the weak nuclear force, and all these basically are much stronger than the gravitational force. All right, so just remember that this is how we can measure their magnitude, compare their magnitudes. So gravitational force is the weakest force out of all these forces. Gravitational force is the weakest force and way more weak as compared to the other four, other three forces. And that's why the other three forces together, they are also called as the standard model of physics. These three together, they are called as the standard model, because they very often can also be studied together, but gravitational force becomes very different from these three. So if you go into the technical details of today's particle physics, you will always also come across uh, concepts where gravitational force is not even considered as a force now. As I mean, if you study particle physics, and if you go through those kind of topics, go into that complexity, gravitational force is not even considered as a force. But let's not go there. I mean, it's way beyond what we are discussing right now, because the entire childhood will be shattered, because gravitational force is the first force probably that you know of, and other forces you might not even have heard until very later. And maybe if you are not from science background, you have never heard of these forces. And gravitation still is something that you might have heard of as a force, but now particle physicists will tell you that gravitation is not even a force. So, but let's not go there, that's completely out of way for us, right? So this is about string theory, because if string theory is proved to be correct, theory of everything perhaps will be proved to be correct, and physics as we know today will be gone, and then there will be new physics that will come up, and the entire NCRTs will then have to be revised. So, but let's look at this question. 2017, they asked you this question in the paper. Please read the question. I'm launching the poll for you. It's a simple question. Please mark your answers. Great. Wonderful to see. 81% of you have given the correct answer. So the terms event horizon, singularity, string theory, and standard model are sometimes seen in the news in the context of. So we just discussed about these two, string theory and standard model. We'll discuss about event horizon and singularity also a little later. In the context of, first is observation and understanding of the universe. This is basically what we are looking at, so should be the correct answer. Second is study of solar and the lunar eclipses, nothing to do with the eclipses. Placing satellites in the orbit, again nothing to do with the satellites. Origin and evolution of living organisms on the earth. It's not only about the living organisms but rather everything in the universe, so that's why wrong. So correct answer will be A. Now, the next discussion is about celestial bodies. So, until now, we have understood some of the basics of the universe, that what is the universe, what is the composition of the universe, what are the various aspects in that composition. So, we discussed about all these things. Now, we come to the next topic about all the celestial bodies of the in this universe. We'll be largely talking about the ones which are more commonly seen or more commonly known celestial bodies. Otherwise, the list is very large of celestial bodies. So the most important celestial body is a star. A star which you can say governs the universe, because there are so many galaxies that are where you have these star systems, and all the celestial bodies largely they are hovering around that star system. So when we talk about a star, what we know is that it is a celestial body that generates light by nuclear fusion reactions and is held by its own gravity. Held by its own gravity. And it has a kind of a spherical shape also because of gravity. All right. Just know this also has, because of gravity. So then in that case what happens is that everything, I mean, whenever you have gravitation forces like this, you will see that gravitationally stability always is attained when you have a spherical shape. So that's why planets are spherical, that's why the stars are spherical, that's why so many other celestial bodies are spherical, because that's where you get a lot more stability than any other shape. So gravity, that's why brings in that factor of spherical shape. Now, when it comes to star, we know that there are nuclear fusion reactions that are happening inside the star. We discussed about this in yesterday's class as well, about nuclear fusion and how nuclear fusion is the source of energy of the sun, and all the heat and light that we are getting from the sun is only because of nuclear fusion. So that goes for any star for that matter. Sun is obviously also a star. Now, when it comes to a star, formation of a star always happens from a nebula. Now, nebula is nothing but, you can say, a region of dust and gases in space. So the picture that you see right here, this is the picture of a nebula. So now when it comes to any nebula, you'll see that these kind of images will always be shown. Very wonderful looking, beautiful pictures of nebula. And what is nebula? The most widely used screensavers and wallpapers of the world. I mean, there was actually a study conducted where they found that nebula is the most widely used picture for a screensaver or a wallpaper. So look very beautiful, and they have all these kind of shapes that look elegant, and hence for that aesthetic value, many a times used as wallpapers and screensavers. So it's nothing but a region of dust and gases in space. Now what happens is that all these dust particles and various ionized gases, they will start coming together, they'll start forming a core. All right, they'll start forming a core. And as all these particles they come together, all these ionized gases they come together, they start forming a ball of mass. As soon as they form this ball of mass, it will have its own gravity because of that mass. Now that it has its gravity, it will start pulling everything towards itself, right? It starts pulling everything towards itself, starts becoming bigger ball of mass, and ultimately this is where the formation of star begins. So first it will form a smaller ball of mass called as a protostar, and from this protostar we'll see that the formation of a star will happen from here. The clouds of dust and hydrogen gas then collapse under their own gravity, and then the center becomes very hot and nuclear fusion starts happening here, and ultimately they will lead to the formation of a large sized star. So this is how the formation of a star happens. Now, one more thing that becomes very crucial for us to understand is the entire life cycle of a star. Now, let me ask you something. Suppose that there is a question, or let's say one of the statements in your paper, which says that when the sun dies, or when our sun dies, it will convert into a black hole. I'm giving you two options. Is it true or is it false? I'm giving you 10 seconds on the poll. Quickly tell me what the answer is. Is it true or is it false? So 56% of you feel that it is true and 44% of you feel it is false. 44% of you are actually correct. The answer is false. This is not true. I'll tell you why. So this is what happens. I mean, let's say we have a generalized notion, generalized information that black holes are formed when a star dies, right? Black holes are formed when a star dies. But it's not that every star, when it dies, it will convert into a black hole. That's not the case. Only the stars which are massive, which are very big, which are very bulky, only these stars, when they collapse, when they die, then only a black hole is formed, or then only can a black hole form. Otherwise black holes can't be formed. Now when it comes to our sun is said to be an average star. An average star, not very big, not very bulky, not very big in size. So that's why it is called as an average star. And when an average star is about to collapse, about to die, they first convert into something called as a red giant. Red giant because they are reddish in color because of lower temperature, and giant because of their size. So red basically signifies low temperature, and giant signifies large size. All right. So first converts into a red giant, and then it forms a nebula, a planetary nebula. Now planetary nebula has nothing to do with planets. All right, just telling you, just because it has a disk kind of a shape, that's why it is called as planetary nebula. uh, it's, I would say, a misnaming by the scientists. They have just created confusion here. It is nothing, it has nothing to do with formation of planets or anything like that. Just that they are a kind of nebula which are disc shaped, hence planetary nebula was the name given. And then lastly they form a white dwarf. They form a white dwarf. So an average star, when it dies, it will form a white dwarf. It will not form a black hole. Every star which has a mass up to 1.44 times, mass up to 1.44 times will be called as an mass up to 1.44 times of the sun will be called as an average star. So let's say if you consider sun to be 100 grams, then any star up to 144 grams will be called as an average star. All right. So every star with mass up to 1.44 times will be called as a average star, as an average star. Now the second kind of star is a massive star. So every star that has a mass above 1.44 times the mass of the sun, they will be called as massive stars. All right, they will be called as massive stars. Now in case of massive stars, when they are about to die, they first convert into a red supergiant. Again, red signifying low temperature, supergiant meaning very large size. All right, so very large sized, very low in temperature, and then supernova occurs. Now this supernova, right, this supernova is nothing but the explosion at the center of this red supergiant. This is basically a violent explosion at the center of a red supergiant. All right, this is called as supernova. And if you remember, we discussed that supernova are the largest sources of neutrinos. All right, they are the largest sources of neutrinos. So entire neutrino world, that I mean all the neutrinos that you have in the world, largest number of neutrinos are formed whenever supernova happens. All right, so I'm just writing it here, just a fact. Supernova are the largest source of neutrinos, right? So supernova occurs. Now after supernova, there are two outcomes which are possible. One, that it can form a neutron star. It can form a neutron star, and if not, it will form a black hole. So the supernova, I mean the red supergiants which are bigger, chances are higher that black holes will be formed, and the supergiants which are smaller, chances are that they would form a neutron star. Now there is no fixed number here where the demarcation is that above this size only black holes will be formed, below this size only neutron stars will be formed. There's nothing like that. There are two outcomes here: either neutron stars can be formed or black holes can be formed. Now neutron stars, just remember, these are the smallest stars. These are the smallest stars in the universe. Right, so this is basically what we see in case of neutron stars and black hole. There's one question that came in 2009. Just read this question. I'm launching the poll for you. Please mark your answers. So 32% of you have said B, which is the right answer. Who of the following scientists proved that stars with one mass less than 1.44 times the mass of the sun end up as white dwarf? This was given by our own Indian scientist S. Chandrasekhar, and that's why this number 1.44, this is also called as Chandrasekhar limit. If you have heard of this term Chandrasekhar limit, then this term basically means this. All right, so this number itself is called as Chandrasekhar limit, and it was named after him because he was the one who proved it for the first time, that if the mass is less than 1.44 times the mass of the sun, then the stars will end up as white dwarfs, and if it is more than 1.44, then in that case they'll end up as black holes, or they can end up as black holes or neutron stars for that matter. So that's why this is something that was proved by him for the first time. Now, coming to what exactly do we mean by a black hole? Now, initially, when we look at the black hole, this was the very first picture of the black hole that was taken back in 2019. Until 2019, we did not even know what black holes look like, what the structure of the black hole is like. Uh, we used to use very beautiful images. I mean, if you just go and Google black holes, you will see wonderful images that Google Images will show you, and these are all artists' impression of what black holes might look like. So this is what, for example, a Google search will tell you that this is what black holes look like. These kind of wonderful pictures they will show you, but unfortunately this is the first picture of a black hole that we had taken back in 2019. Now, when we talk about a black hole, now understand what exactly a black hole is and why the term black hole is being used here. All right. Now, in case of black hole, two terms: black, hole. Why black? Black because of absence of light. Because what we say about black holes is that these are regions which are so strong in gravity, they have so strong gravitational force that even light cannot escape them. Light cannot escape them, and that's why this is an area marked by absence of light. Area marked by absence of light. That's why the term black. All right. That's why the term black. And then the second term is whole. Why the second term is whole is mainly because you can say that it's just like a well. So for example, let's say if you look at any well out there, you'll see that there might be a small boundary all across the well, and if somebody crosses that boundary, you will know what will happen. Don't try that at home. So anyone who crosses the boundary will simply fall into the well. So something similar happens in case of a black hole also, that there is a boundary of the black hole, and any particle, any source, anything that crosses that boundary will just fall into the black hole. So that's why the term hole is being used, black hole. All right. So that's why black hole, black because of absence of light. This is because of absence of light. And the term hole is being used mainly because that particles near it fall into the black hole. So if you look at the structure of a black hole, it looks something like this, that there is this thing which is called as event horizon. All right. Now event horizon is like the boundary of the black hole. Event horizon is like the boundary of the black hole. Boundary of the black hole. Anything that crosses the event horizon will fall towards the center of the black hole, will fall towards the center of the black hole, which is called as singularity. This is called as singularity. So as you can see here, you have depicted singularity here. So singularity is basically the center of the black hole. Center of the black hole. So now what we basically see is that uh, anything that crosses the boundary, anything that, let's say, crosses this boundary of the event horizon will simply fall towards the center of the black hole. All right. So this is basically what we understand about a black hole. So black hole, basically you can say that black holes are places in space where the pulling force of gravity is so strong that even light cannot escape. Now when we say light cannot escape, the meaning is that the light particles, they also fall towards the center of the black hole. All right. the light particles fall towards the center of the black hole, and hence they become invisible, and hence this region becomes entirely black, entirely dark. Now, this picture that we saw here, this was a picture that was taken with the help of a telescope program called as the Event Horizon Telescope. Event Horizon Telescope program is the telescope program that took this first picture of the black hole. So in a manner, you can say that it is depicting the event horizon, because you still cannot see what's in at the center, right? We can't see what's there at the center. The center still remains dark, but we have basically taken a picture of this entire event horizon, right? The boundary of the black hole around it. So as you can see, that movement of light is happening all across this center or the boundary of the black hole. Now this event horizon telescope program, this basically Event Horizon Telescope program captured the first image of a black hole called as M87 in 2019. So in 2019, this first picture of a black hole was captured with the help of this picture that we saw right here. And then after that, there is another picture that they captured last year, which is of Sagittarius, not last year, 2022, of Sagittarius A star. So this also picture taken in 2022. So this is a supermassive black hole which is at the center of our Milky Way galaxy, Sagittarius A star. And this picture also has been taken in 2022 with the help of the Event Horizon Telescope program. Now, when it comes to the Event Horizon Telescope program, this is very unique telescope program because it is not one telescope. All right, it's not one telescope, but rather 10 telescopes which have been placed all across the globe. And what we are trying to do here is that we are trying to increase the aperture of this entire telescope by adding the apertures of all the individual telescopes. Now understand some basics here, that when we talk about the aperture, now when it comes to the aperture of any, let's say when you are talking about any camera, all right, even if you talk about the camera of your phone or of any camera that you might have, aperture becomes a very very crucial aspect of any camera, because when it comes to the aperture, it becomes very crucial because it will uh, let the light come through the camera. All right, it will let the light come through, and if the aperture is large, then it will let more light come into the camera, and then in that case you can take pictures even in very low light. So for example, let's say today, uh, if you have an expensive camera phone, then you'll see that they have night mode pictures and dark mode pictures and so on, where even if you have pretty much dark environment, even then they are able to capture the images, they are able to process the images, because what they do is they try to make the opening as large as possible so that more light can be let into this, and the more amount of light, the higher the chances that the camera will be able to take pictures in that scenario. So that's why this aperture becomes very very crucial. So now what we are trying to do in this case of this telescope program is that we are adding the apertures of all these individual uh, telescopes, so that a larger aperture which is equivalent to the entire earth is being formed, and hence it will let light come in. And that's why, because of this, even the areas which are very dark, or let's say very small amount of light is also present, it will be able to capture those areas as well. And that's the reason why it was able to capture an image of a black hole. Otherwise it could not have captured the image of a black hole. But now we see that first M87, also called as Measure 87 star, this for the first time was captured in 2019, and then Sagittarius A star also has been captured in 2022. Now comes another very very important topic, and this is the topic of gravitational waves. Now when it comes to gravitational waves, this is again something that for the first time was predicted by Albert Einstein. Now prediction happened in 1915, and finally we were able to observe it almost 100 years after this. So that's why he was able to figure out the gravitational waves a century ago without even using any technology that we have today. So that was the genius of this particular scientist. Now, when it comes to gravitational waves, first and foremost, let's try to understand what we mean by gravitational waves. And it has been a topic which from where 3 4 questions have come in the past 10 years. Now this is also something that has to be taken as an important strategy for your examination, that when it comes to the kinds of questions, the kinds of current affairs that often will be asked in your examination, you have to understand that a random current affairs is not normally asked. Let's say gravitational wave, why it's a very very important example of what to prepare for. Until 2014, until 2014, UPSC has never asked a question on gravitational waves. Since 2014, I can count 1 2 3 and 4 questions which are directly or indirectly related to gravitational waves. So 10 years, 4 questions. Before that, 40 50 odd years, 0 questions. Do you think why? Do you know why? What's significant for 2014? What changed in 2014? Do you know with regards to gravitational waves? LIGO mission, yes, detection of gravitational waves happened. More importantly, Nobel Prize was given. All right, Nobel Prize was given for finding or observing gravitational waves. So that's what changed. And since then, UPSC has been asking questions on it. So just remember, that's why what happens then is that these kind of things which were just theories, where a lot of experiments were happening, a lot of people were trying something or the other, all of that changed as soon as the first observation happened. The observation happened, the Nobel Prize was given, and it becomes an important topic, right? So that's why you have to consider when something becomes important. Something that is just a theory will never be a very important topic. Something that has been proved, something that has been established, now becomes an important topic for your examination, especially in the context of science. So gravitational waves, what do we mean by gravitational waves? We are saying that these are gravitational waves, meaning that these are waves of gravitational origin, which have a gravitational origin. Now when we say gravitational origin, the meaning is that they are formed because of gravitation, right? They are formed because of gravitation. So in this scenario, whenever there is something very massive, something very highly energetic, then in that case you will see that formation of gravitational waves will happen. Collision of two stars, merger of galaxies, merger of black holes, collision of black holes, supernova, very strong supernova. All these are events which are very massive. These are events which are very highly energetic. So in these kind of cases, wherever you have something very massive, you'll see that this is where there is a possibility that gravitational waves might be originated from there. So that's why I'm saying merger of galaxies, merger of black holes, collision of black holes, collision of stars, merger of stars, collision of galaxies. So all these kind of events where you have something very massive happening, then in that case you will say that this is where gravitational waves could, or gravitational ripples can come out from there. So overall, this is basically what we see for gravitational waves. So why gravitational waves? Because if you look at this first picture, what you see is that uh, just understand this, that when we imagine the entire space, we think of it like a mesh, like a net. Just think of the football goal post. It's just like that football goal post where you have that net into which the football is kicked. Now what happens as soon as you kick the football into the post? What happens? That waves will be formed out of that net, right? Waves will be formed out of that net, and the force with which you kick that football will determine what kind of wave come out of it, right? So if let's say somebody has kicked the football with a lot of force, the waves will be more violent. And if somebody has just nudged the ball into the net, then waves formation will be little lesser. So just imagine that instead of having that football, suppose that you have a football made of iron, and that football made of iron is what you kick into the net. what happens then? First you break your leg, but then the ripples that will be formed will be very violent, correct? And instead of that, let's say you take a very small stone and you throw it towards the net, what happens? Almost nothing. So something similar here. Planets in the context of gravitational waves are very small compared to black holes or entire galaxies or merger of stars or collision of stars. A planet or a small celestial body is nothing there. So that's why the ripples will not be observable from a small planet. But let's say when you have a binary star system like this, or all the examples that we discussed, in those cases, the kinds of ripples that will be formed, they will travel very long distances in the space. And these are the kinds of waves that we can actually detect. Otherwise, it's almost impossible for us to detect gravitational waves. Now, the first time the gravitational waves were detected, which was with the help of this one establishment called as LIGO, Laser Interferometer Gravitational Wave Observatory. So this is where we saw that first observation of a gravitational wave was made. And after that, there have been other projects. For example, India right now is working on Indigo LIGO, because Indigo LIGO is a project where now India has started working on, and where last year even the budget has been approved for going forward. Declaration happened almost 4 5 years back, almost 6 7 years back now, and the budget allocation and the improvement of the budget has been done just the last year. So now Indigo Ligo comes into existence. There have been other projects also. So for example, there has been a LISA project, also called as the ELISA now, Evolved Laser Interferometer Space Antenna. So this is basically another gravitational wave observatory. Gravitational wave observatory kept in space. Now, why we have kept it in space is mainly because we wanted to get away from the gravitational field of the Earth. Because gravitational waves are gravitational in nature, and Earth has a very strong gravitational field. So, in the presence of very strong gravitational field, it becomes very difficult for us to detect an incoming gravitational wave. So that's why this is another variation of the LIGO or the Indigo, etc., where you have a laser interferometer, or let's say a gravitational wave observatory kept in space away from the gravitational effects. So this is Evolved Laser Interferometers Space Antenna. Now, surprisingly, UPSC has asked two questions only on ELISA. Never expected, but two questions actually have come on ELISA. So going forward, I don't think it should be an important topic, because something where they have asked two questions in 5 years, I don't think they are going to repeat again. But just know that this actually happened. Two questions actually came from here. Another question which was asked in 2019. Just read this question. I'm launching the poll for you. Please mark your answers. Great. So almost 70% of you have given the correct answer, which is B. Recently, scientists observed merger of giant black holes billions of light years away from the Earth. What is the significance of this observation? Merger of giant black holes. This is the key phrase for this question. Now, whenever merger of giant black holes happen, without any exception, gravitational waves will be generated from there. Do you have any doubt on this? Right? What we discussed is wherever you have anything very violent, very massive, gravitational waves will be generated from there. So that's why whenever merger of giant black holes happen, it's a rule that gravitational waves will be generated from there. Now look at the options. First says Higgs boson particles were detected. Now Higgs boson is related to particle physics at the subatomic level. We are talking about giant black holes and merger of giant black holes. So nothing to do with Higgs boson particles. This is wrong. Gravitational waves are detected. Looks to be correct. Let's come back on it. Possibility of intergalactic space travel through wormhole was confirmed. Now, this only has been confirmed in movies like Interstellar, etc. Beyond that, it has never been. This has remained science fiction. Enabled the scientists to understand singularity. Now, although singularity is related to black holes, but it is not about understanding of the singularity. We know what singularity is, we understand what singularity is, so that's not something which was new. So that's why this is not the answer. The correct answer will be gravitational waves were detected. So just know as a rule that whenever something violent like this happens, gravitational waves will be detected. So you don't even need to know the current affairs. For example, this happened in December 2018, and hence the question was asked in 2019. But what I'm saying is that you don't even need to know current affairs to answer this question. It's a theoretical question, I would say, that wherever this kind of an event happens, gravitational waves have to be generated from there. All right. So that's why correct answer will be B. Now, coming to the next important topic, and here we are talking about our sun. Now, what we say about the sun is that it is a main sequence star. It is a main sequence star. Now, main sequence stars basically is another name that we use for average stars. All the average stars are also called as main sequence stars. Now, when it comes to the sun, we know that the sun basically is at the center of the current affairs, uh, because you will see that whether it is Aditya L1 mission, whether there are all these solar winds and solar flares and geomagnetic storms, etc., that have been constantly in the news. Because of that, I would say that the sun is at the center of the current affairs right now. Last to last year, they did ask a question on the sun, and I expect more questions are about to come from the sun. They can ask something related to the sun. So that's why some of the basic concepts related to the sun, they become very, very crucial. We know that the entire solar system is bound by the sun. All the planets, etc., they revolve around the sun. Correct. Now, with regards to the sun, first and foremost, understand the basic structure of the sun. We start from the core, and core is where all the nuclear fusion occurs. This is where nuclear fusion occurs, and hence this is the source of all the heat and light from the sun. Source of heat and light. So this is where it all happens. The temperature will be very, very high. The temperature can be of the order of 15 to 20 million degrees Celsius. All right. So temperature will be very, very high, and fusion would occur in these kind of places. So temperature can be 15 to 20 million degrees Celsius. Then after that, we have the radiative and the convective zones. Now these are zones through which all the energy being generated, all the heat and light being generated, all the radiations being generated, they are traveling outward. They are traveling towards the edge of the sun, which is the surface of the sun. So, so that's why these are the zones through which the energy is passed outward. Now, photosphere basically is the surface of the sun. Photosphere is the surface of the sun. So surface of the sun meaning that this is where, I mean, the outer part, this is the outer part of the sun, Now photosphere, by the time you come to the photosphere, the temperature now decreases to almost 5500 to 6000 degrees Celsius. Obviously, because we have now come out of the sun, almost out of the sun, right? Away from the center, away from all the heat and light that was generated, all the source of that heat and light. So obviously the temperature decreases by the time we reach the photosphere or the surface of the sun. So that's why from 15 to 20 million degrees Celsius, now the temperature has dropped to just about 5500 to 6000 degrees Celsius. Then after that comes the atmosphere, the outer part of the sun, as you escape out of the sun, where you have two parts called as chromosphere and corona. Now chromosphere and corona, these are the parts of the atmosphere, and these are the things that are visible when you have any solar eclipse. If you observe a solar eclipse, you will see that at the time of a total solar eclipse, you have a ring like structure, right? A ring like structure is visible, the sun is not visible. Have you seen it? Have you seen the pictures? Or maybe you might have seen it at the time of any solar eclipse, that only the ring is visible, a red colored ring is visible, and the entire surface is not visible. So that ring that is visible at the time of a solar eclipse, it's nothing but the atmosphere of the sun. So this is basically visible during solar eclipses. And that's why the term corona. Do you know the meaning of the term corona? What does corona mean? Why do we call the virus also as coronavirus? Yes, Alita, you are correct. Gayatri, you are correct. So corona basically means crown. All right. The meaning of the word corona is crown. So because there is this ring-like structure, which is something that can be associated with the looks of a crown. So that's why the term corona is used, because that looks like a reddish-colored crown. So similarly, in case of coronavirus also, because there are spikes that you have which look like a crown, and hence the term corona has been given. All right. So that's why it is like the crown of the sun, hence the name corona. Now, what happens here is something peculiar, that as we come out of the surface, when we are escaping out of the surface, the temperature should have decreased further. There is no source of this of any kind of energy or anything like that. So in that case, the temperature should have dropped further. But what we observe is that as you come to the chromosphere, the temperature increases. The temperature goes to almost 50,000 degrees Celsius, and by the time you are in corona, the temperature can go as high as 1 million degrees Celsius. All right, so from 5, so first it was 15 to 20 million degrees Celsius, dropped to almost 5000 degrees Celsius, and then again rises to almost up to 1 million degrees Celsius. Why does this happen? Thankfully we don't know. We don't have an exact explanation to why exactly this happens, and for it's good for you that you don't have to learn about it. And this is where all these missions that we have launched, they are going to help. The Aditya L1 mission, for example, one of the major objectives of Aditya L1 mission is to study the atmosphere of the sun and understand all these anomalies that we see on the sun. To understand the atmosphere, to understand all the activities in the atmosphere of the sun, one of the major objectives of Aditya L1 is this. Similarly, there was a Parker solar probe that was launched a few years back by NASA. And this Parker solar probe also has gone very near to the sun. And again, the primary objective that they have taken is to study the atmosphere of the sun and understand everything that happens at the atmosphere. So that is basically what we see here. All right, so that's why all these are the various regions of the sun. These are the regions of the sun. Now, related to the sun, there are certain phenomena, and these phenomena can also become important for your examination. Sunspots, solar flares, and solar winds. What do we mean by these? I forgot, I wanted to bring a picture. Recently, I was just zooming with a camera. I was zooming into uh, the picture of the sun, towards the sun. It was very densely foggy that day, so taking the picture of the sun was possible. And when I zoomed into the sun, I saw a sunspot. I forgot to bring that picture. Maybe I'll try tomorrow and bring that picture. I processed that picture and I was able to spot the sunspots. So so let's try to understand what do we mean by sunspots, solar flares, and solar winds. Now, sunspots basically are, as you can see here, sunspots look like spots on the surface of the sun, black colored spots on the surface of the sun. Now, these sunspots are formed when temperature of a certain area on the sun is lesser than the surrounding areas. So, for example, let's say the surrounding areas have a temperature of suppose 5500 to 6000 degrees Celsius normally, right? Now, in case of these sunspots, the sunspots will have a temperature which is lesser, maybe in the range of 3500 to 4500 degrees Celsius. So now, because they have a lower temperature, that's why they appear to be darker. They appear to be darker because of that. And these sunspots, they can be formed because of various different types of activities on the solar surface. So maybe sometimes what happens is that a lot of energy is just released out of the sun, just explodes out of the sun. And when that happens, it just leaves behind an empty space. And that empty space, because of lack of energy, will have lower temperature, and hence it will have uh, a dark, it will look darker. So hence these look like spots on the sun, but these are not like spots. These are very big areas. They are bigger than, you can say, the entire earth in size. Now, uh, another very peculiar thing about the sunspots is that they actually have an 11-year cycle. Every 11 years they would appear at the same spot. So for example, if the sunspots have appeared here today, then 11 years later, the sunspots will again appear at the same place. All right, they'll again appear at the same place. So they follow an 11-year cycle, and this is also called as the solar cycle. So when it comes to the sunspots, this is what a sunspot would look like. The sunspots basically are dark, cooler areas that appear on the surface of the sun, and they are caused by intense magnetic activity on the sun's photosphere, because of which a lot of energy might be ejected out of the sun and leaving behind these kind of areas. And normally, as I told you, that the temperature range for them will be in the range of uh, 3500 to 4500 degree Celsius. Now, when it comes to the sunspots, as we discussed, that they follow the solar cycle, which lasts for around 11 years. So 11 years later they will again form at the same place. So overall, this is basically what we see, that energy and magnetic field lines, etc., will be ejected out of the sun, and hence they will form these sunspots. After this, we have these solar flares. Now these solar flares, as you can see, that these are like flares which are coming out of the sun. They are being uh, these are high energy particles, magnetic in nature, which will come out of the sun. Now, as these charged particles and energy, they come out of the sun, this is where we see that they also carry a lot of energy with them, a lot of radiations with them, and hence the temperature also can be higher, but largely they would have very strong magnetic effect. They would have very strong magnetic effect, and so strong magnetic effect that can be felt even on the earth. Even on the earth, we will be able to see these effects. So these are like big explosions that happen on the sun surface. So they originate at the surface, but largely this is something that we will see in the corona. This is something that we will observe in the corona of the sun. All right, so corona, that is the atmosphere of the sun, is where they would just extend, where they will be completely visible. Now, overall, it happens when the magnetic energy is suddenly released. That's why it's like an explosion. The energy particles, they just explode out of the sun. So that explosion is called as solar flare. Now sometimes solar flares are also related to sunspots. So I'm just writing Solar flares may lead to the formation of sunspots. Now just remember, what I'm saying is may lead to. I'm not saying will need to. I'm not saying that they are always associated. I'm saying that solar flares can become one of the reasons for the appearance of sunspots. Just remember this, all right? Now, when the solar flares occur, obviously a lot of energy is released. So that's why a, a lot of X-rays, ultraviolet light, and even charged particles like protons and electrons also can be released, and they can last from a few minutes to a few hours. And as I told you, that they can have an effect on the Earth also. They can have an effect on the Earth also, and that's why they can create beautiful auroras as well. Aurora borealis, as we call them, and we'll just discuss about them also. So they can lead to the formation of aurora borealis also. Then we have solar winds. Now, in case of solar winds, these are magnetic winds. And since they are magnetic winds, they can also interact with the magnetic, you can say, magnetic field of the Earth. So there can be an interaction between them, and hence you can say that solar winds can also affect the magnetic fields of the Earth, and hence they can have a negative impact sometimes also on the Earth. Now, overall, when it comes to solar wind and solar flares, understand one very important difference between the two, that in case of solar winds we are talking about a constant flow of charged particles. In case of solar flares, what do we say? Explosion, right? A sudden explosion of particles out of the sun. In case of solar winds, we are saying it's not an explosion, it's a continuous flow. It's a continuous flow of charged particles and magnetic particles out of the sun. So that's the most important difference between a solar wind and solar flares, because they can have same particles, they can have the same effect, they might have the same reason as well, but solar flares are like explosions, whereas solar winds are a continuous flow of charged particles. That's the most important difference between solar flares and solar winds. Remember this. Now, they are primarily composed of protons and neutrons, the charged particles which were there also in case of solar flares. And again, they also are emitted from the sun's outermost layer, that is the corona. And in this particular scenario also, they can also have an impact on the Earth. So for example, when we talk about this phenomena of auroras, you might have seen these kind of pictures called as aurora borealis. Aurora borealis, and then there is another term called as aurora australis. Have you heard of these terms? Aurora borealis and aurora australis. You might have seen these kind of pictures where the entire sky looks to be greenish in color, or sometimes pinkish in color as well. So in the north, it is called as northern lights as well, popularly. And this year, I mean, for those of you interested, 2024, especially 2024 and early 2025, is the maximum of solar activity. So solar activities are going to be very intense this year. So if you want to observe aurora borealis and aurora australis, this is the year. Book a ticket for Norway after your mains examination. Oh, you have interviews also. So then I think you'll have to see only the pictures. But if you go there, probably this is one of the best years to see it. All right. So aurora borealis and aurora australis. Now, aurora means what? Aurora means colors, right? Aurora means color, related to color. And borealis, where are we getting this term borealis from? So it comes from the term boreal. You might have heard about the boreal forests. So the Arctic region is called as the boreal region. Boreal means Arctic. Boreal means Arctic, and hence this region is called as the boreal region, and hence the vegetation in the Arctic areas, they are also called as boreal vegetation or boreal forest, etc. Right? So that's why in this particular scenario, aurora borealis, because these are the colors that you see in the northern uh, northern areas, right, in the Arctic areas. That's why aurora borealis. And similarly, aurora australis mainly because of Australia, because it is seen in the southern hemisphere. So in simple terms, they could have called it as northern light or northern colors, etc. But then you would not need people like me to explain you the terms. That's why scientists make things always difficult by using Greek or the Latin terms instead of using simple English. So this is basically what it is. So it can have a negative impact on the earth as well, because anything magnetic, electrical, or electronic can be negatively impacted by solar winds and solar flare. All right. So that's why just remember that they can be negative impacted. For example, let's say any satellite in the orbit, they can have a negative impact. Even power outages can happen, electrical impact. Satellites can have a negative impact. So their aircrafts may find difficulty, communication systems might find difficulty. So there are all these problems that can occur whenever you have solar maximum, whenever you have intense activities from the side of the sun. So that's why there are all these issues that they can lead to. This was asked in your 2022 paper. Actually, it's a very simple question, I would say. Please read the question and then I'll launch the poll for you as well. Please mark your answers. Hmm. So 60% of you have marked the correct answer, which is C. Let me just discuss this with you. If a major solar storm, that is solar flare, reaches the earth, which of the following are the possible effects on the earth? First is GPS and navigation systems could fail. This is correct. We discussed that anything that is electronic or magnetic in nature can fail. So this is electronic anyway. So yes, this can occur. Tsunamis could occur at equatorial regions. Now, first and foremost, we are talking about tsunamis, and second, we are talking about the equatorial regions. Now, tsunamis largely happen because of seismic reasons, right? Whenever earthquake kind of a situation happens inside the sea, this is when tsunamis can occur. So, tsunamis do not happen because of magnetic effects. The only thing that solar storm or solar wind can cause is a magnetic effect. So magnetic effects do not produce tsunamis. So that's why this is wrong. And that too, we are talking about equatorial regions. What will be the effect? What will be the major effects? The major effects will be where it will be in the on the poles, right? The north and the south poles, because these are the magnetic regions of the earth. Equatorial region is not. So even if these effects happen, the effects will happen largely in the polar areas, not the equatorial regions. So that's why second statement is wrong. Third statement is power grids could be damaged. This is correct. We discussed that anything electrical can be affected. So, and this we have seen last year, it was in the news also that in New Zealand some power outages happened because of solar flares. So that's why this is also possible. Intense auroras could occur over much of the earth. This is also correct. Last year, I mean 2023, we saw for the first time that even in Leh, in Ladakh region also, for the first time auroras were observed. Even you might have seen that even in England, in Britain also, this was observed because the intensity was very high. So that's why this is also correct. Forest fires could take place over much of the planet. Now, how forest fires cannot happen? Because forest fire means what? That temperature has to increase so much that it leads to forest fires. That's not the case, because these are magnetic. Remember, these are magnetic lines. It's not that heat of the sun is coming to the earth. Because then, if that's the case, why only forest fires? We will all be roasted if that was the case. So, not only forest fires. So that's why nothing to do with solar intensity at all. Orbits of the satellites could be disturbed. This is also correct. So this was magnetic in nature. So that's why this happened. This can happen, I mean. Then orbits of the satellites could be disturbed. Again, correct. Shortwave radio communication of the aircraft flying over polar regions could be interrupted. So this is also correct. So 2 and 5 are wrong. So correct answer will be C. You will get the answer from the second statement itself, because you have second statement here, here, and here. So that tells you that this should not be the correct answer. So this question, that this was asked in your 2022 paper. Any question if you have with regards to whatever we have discussed in the last 1 hour? Because I believe we do not have enough time that we can complete this new topic. And anyway, it will take some 10 minutes to solve your questions as well. There is a mistake in PPT. Solar flares do not come from the corona, but rather come from the solar surface. Solar. I wrote the same thing, I think. Yeah, this is what has been written here also, that they are big explosions that happen. I mean, their origin is always at the surface, just that I mean, they would be visible all across in the atmosphere. So but the origin is at the surface. So we both are basically saying the same thing. If a star is millions of light years away from the earth, does that mean that even if it died a million years ago, we can still see it? Yes, absolutely, absolutely correct. What is the difference between electric and electronic? Okay, so see, between electrical and electronic, although they're almost similar, but basic difference is that when you are talking about anything electrical, it's more about the flow of charge. All right, it is more about the flow of charge and flow of, you can say, the movement of electrons, the vibrations in electrons, and something that leads to conduction in certain material. So that is electrical. Electronics is when you are trying to control those electrons, when you're trying to control the flow of electrons in a manner to do a specific task. So that's the basic difference in between electrical and electronic, although they are very, you can say, overlapping in the way, because both have the same source, that is electrons. But one is about the continuous flow of electrons happening and leading to the conduction in material, and anything that is happening, you are trying to just use it. Whereas in case of electronics, you're just trying to also control that flow. You, in electrical, I mean, in any electrical device, we do not try to control that flow, but in case of electronic devices, we try to also control that flow. So that's a basic difference between the two. Otherwise, more or less, they are related to the same thing. Auroras are caused due to solar flares or solar winds, both. Solar flares and solar winds both can lead to auroras. Reason for solar eclipse: solar eclipse happens when the moon comes between the sun and the earth. After falling into the black hole, where will the material go? It will not really go anywhere, it will just become a part of that black hole, it will become the part of that dense center. Its entire structure changes, and there are a lot of structural changes that will happen in matter when they are at that position in the black hole. Which chapter in NCRT to refer for this? I don't think there is any chapter in NCRT to refer for this. If at all, I think in class 11th geography book, some of these topics have been covered, but not all, only few. Last option I can't understand in the question. Last option. Shortwave radio communication of the spacecraft flying over polar regions could be interrupted. So what I told you is that anything electrical, electronic, or magnetic in nature can have a negative impact. So communication systems are based on radio waves. Radio waves anyway means electromagnetic waves, meaning they have electrical and magnetic properties. Hence, they will be interrupted, and especially over the polar regions, because polar region is where the magnetic intensity is the highest. So that is why they will be affected. Is it possible in the future to travel in the sun from sunspot? I wouldn't say that, because before reaching that sunspot, you have to first cross the atmosphere, and that atmosphere itself is having very, very strong radiation presence, and also very high temperature. And escaping from all that is, at least for now, it's extremely difficult. Gravitational force of black holes, it's extremely high, because you have very dense material present there and in a very small space. So the gravitational pull is very strong. If the seventh option is an equator, then we would mark it as wrong. Then we would not say that this is correct. Cannot understand CMB. Cosmic microwave background, what we are basically saying is that when we observe the outer space with the help of certain instruments, we are able to observe microwaves in the background. We can see microwaves in the background. So those microwaves that we see in the background, they tell us about the heat presence of the early atmosphere. So that is why in the background, because when you're looking into space, you are also actually looking through time. All right, because then only the light from something that was very long ago will have taken more time to reach you. So in a manner, we are looking back in time when we are looking towards the outer space, and that's why these kind of instruments are able to see that microwave in the background. Please explain string theory. String theory, we are saying that every particle, according to string theory, is made of tiny uh, strings, and there are vibrations in these strings which will lead to the formation of all the particles that we know of. With nuclear fusion only we make nuclear bomb? No, nuclear bomb largely is made out of nuclear fission, not fusion. What are stellar stars? I'm not sure what is a stellar star, because stellar is a word that is used for a star. What was that orange color in the black hole? Orange, basically orange yellowish color that we see there, that's the light that we are looking at when we are capturing the picture of the star, I mean of the black hole. Can air force or commercial plane fly in space? There actually are some companies which are now offering you a trip to space. I mean, you can book that. For example, I think it's uh, uh, I'm forgetting the name of the company. There are a couple of companies which are giving you that option, that pay 50 lakhs and they would take you to the space for like 15-20 minutes. So if you have that kind of money, why not? But if you have that kind of money, why even prepare? Jupiter size exoplanet form. Yes, we'll discuss about exoplanets tomorrow. How are solar flares formed? Solar flares are formed basically when the solar intensity, the magnetic intensity, all of a sudden rises a lot at the surface of the sun, and that leads to ejection of particles also. Sometimes that's why they are related to something called as coronal mass ejection. That what happens is that the magnetic intensity increases a lot, and this leads to a lot of charged particles being emitted from the surface of the sun, and that is what leads to solar flares. There are four fundamental forces in nature. Is dark energy within the purview of these four forces, or is it a separate force? It's not a force, first of all, it's a form of energy. And right now, we haven't been able to establish any kind of relation between the two. I do not understand the second point, the last question. Why is it wrong and solar flares don't cause it? Because solar flares are magnetic particles. Tsunamis do not happen because of magnetism, right? It has nothing to do with magnetism. It has more to do with the tectonic movements and the seismic movements below the earth. So that's why it has nothing to do with the forces coming from the sun. Leaderboard, all right. This is today's leaderboard. So congratulations to all of you who have given the correct answer. All the correct answers. For those of you who did not, I hope that you learned and you'll not commit a mistake later. Yes, session is done. I mean, we have a lot of questions pending from you, and that is what I'm just looking through. After falling in the black hole, where will the material go? They would just be there and they would then just spread out into the space as energy and mass particles. So 16 of you have given all the correct answers. That's great. Please check the second point of solar flares. Second point of solar flares. So basically, we are talking about that. See, understand the basic difference. Origin is where origin is at the surface. They spread out from the surface, but they spread into the atmosphere. They spread into the atmosphere and into the corona, from the chromosphere to the corona. So that's where there is a base. These 2 points that we have shown here. Those who don't have doubts can leave. Of course, you can. No issues. 2024 solar cycle happening, not solar cycle, but maximum of this solar cycle, you can say, in 2024. Electrical devices use conductor, but electronic devices use semiconductors. Yes, largely true. How to be strong in science and tech prelims question. The I mean, the basics, whatever we are discussing, that has to be strong, and some of the concepts that you see in current affairs every now and then, that should be strong. Aurora australis appears from Tasmania and northwest New Zealand. Yes, it happens there. We predict for certain whether a red supergiant will turn into a neutron star or a black hole? Is there any specific formula for ascertaining this, much like the Chandrasekhar limit? Not really. It's a very complex situation out there, because of which we do not really have an exact demarcation of how to predict whether a neutron star or a black hole would be formed. Neutron star and simple star is the same? No, they are not same. They are little different. As giant stars after their death become neutron star, can we say that death of a big star leads to birth of smaller star? In a manner, yes, you can say so. There are a lot of questions that you asked. Many of these questions, I see that I've already given you the answers. Many of you have written the same question twice or thrice. Please explain again why polar and not equatorial regions are affected during solar flares. As I told you that uh, the magnetism of the earth exists at the north and the south poles more as compared to the equatorial regions, where it is devoid of the magnetic intensity. So that's why. I think many of these are all the repeated questions. You should ask your question once only, because see, I'll just go through all the questions one by one. I try not to skip anything. By chance I might, if that has happened, you can ask later, but more or less I'll answer every question that you have here. All right, so if you have any further doubts, please let me know. We'll have a discussion tomorrow. Please also go through everything that we discussed. If you have any doubts, you can always bring it back tomorrow, and we shall have a discussion on the same. So, with this, let's end the session for today. Thank you very much for being here. Please go back, revise everything, and be back tomorrow. And if you have any doubts, you can always bring it back in tomorrow's class, and we shall have a discussion on them. Thank you.